First of all, I would like to thank the organizer for giving this opportunity to present some of our recent work. So today what I am going to talk about the different kind of designing of the topological phases and how we can understand their responses in general, and the most of the work done by my student Shweta, present student Shweta, and the former student Shurosri, who is now in US for her postdoc. Okay, so technically I am classify the designing part of the topology in the two sector, as in a non-magnetic system or non-magnetic topological phases, and as well as the magnetic cases where I have a broken time reversal symmetry. And I have we classify as a 4 different part or 4 different way to design the topological phases. First is what I am going to talk about, the Rashba state, how I can design the Rashba state in the layered system of the KCDBI, and then we will go to the how we can introduce or do the topological crossover from the gapped to gapless by the tuning the interactions. These two are the non-magnetic system, and if we go to the magnetic topological phase and how we can enhance the anomalous Hall conductivity by the straining or the thin film geometry, and the last, if we design the heterostructure, how I can enhance or induce the anomalous Hall conductivity in the heterostructure engineering. Okay. So first what I am going to talk about, how we can basically interwing the topology and Rashba in a layered system. This work is done in collaboration with Professor Tanushree Shah Dasgupta. Okay. So I need not to introduce any of the topological phases in this audience. So, but just one is a zoo of the topological phases where you have a gapped, you have a gapless, and most of the time are the basically symmetry tuned. Okay. So, however, what is the Rashba effect? Rashba effect is nothing but a spin splitted bands in the momentum space, and the in the case of the degenerate spin state, which is a non-magnetic, if you have a where you have up and down spin are degenerate. If you have a Zeeman kind of splitting, you have a splitting in energy bands in the energy direction. However, in the case of the Rashba splitting, you have a momentum dependent spin splitted band with a kind of spin textures. Now, why we basically want to stitching of the topology and the Rashba effect. So technically, if in the case of the Rashba effect, we have a spin splitted band even in the absence of the or in the presence of the time reversal symmetry, that means in the absence of the magnetism. As a result, it can be used as a kind of filtration process of the spinotronics, where we can start with a kind of 2D material, and if we can have a shortlist few of the topological system, and if we can induce the Rashba state and with a large Rashba effect, then we can have a kind of topological spinotronics system. Okay. So this is a KCDBI system, which is a kind of ABX, in general is a ABX compound, and depending on the B site, which is a in the case of the CD, B site, either it is crystallized in a hexagonal space group or in a tetragonal space group. For example, KZNBI or if it is a zinc based system, it is usually synthesized in a hexagonal space group, and if it is a cadmium based system, is a tetragonal space group. Now, how it is geometries looks like is a cadmium is surrounded by the bismuth, and the potassiums are placed as a spacer. And important thing is a crystallized in a non-symmetric space group with having a glide and the screw axis. Now, if we just do the electronic structure, and we can see there is a lot of band crossings, and some of the band crossings are the rotational symmetry protected, and some of the non-symmetric symmetry protected band crossings. Now, if we include the spin orbit coupling, there is this very small tiny gap is opening up close to the Fermi energy, whilst the non-symmetric symmetry protected state, protected crossing still preserve. And as a result, we can have a kind of topological semi-metals with a small hole pocket and electron pocket in the presence of the spin-orbit coupling. Now, if we characterize the topological phases, and we can find it is a non-trivial strong topology with a non-trivial one-year charge center, which is nothing but a Berry curvature in some sense, and have a non-trivial topological surface states. So, bulk KCdBi is a topological semi-metals with a robust surface states. Now, what we can do some kind of confinement engineering. That means we can make a layered system out of the bulk KCdBi, and we can calculate the cleavage energy, which turns out to be very small. That means is highly cleavable. If we put in the perspectives of the other 2D systems, they are very similar range. So that means although is a 3D system, but is highly cleavable and can be converted as in terms of the 2D materials. Now, what happened to the electronic structure if we make a kind of 2D version of this thing? If we go to the spin orbit band structure, important thing is now there is opening up a gap at the Fermi level. And if we characterize the topological phases, indeed have a topological insulator with a bulk gap and the conducting surface states. So that means if we go from the bulk system to the 2D, I can create a kind of gapless to a gap topological phases, as well as the topological semi-metal to a topological insulator. Now, since it is a 2D system, is an intrinsically broken inversion symmetry, if we apply electric field on it, then we can find out nice Rashba kind of band structure, both in the conduction band as well as the valence band. But this Rashba bands is a asymmetric Rashba, where you have a kind of in the case of the conduction band and valence band in both. Now, if we just increase the strength of the electric field at about 0.3 electron volt per angstrom, what we found from the gapped system, it's again become a gapless. So that means by tuning the electric field, technically I can go from an insulating state to a metallic state, keeping the Rashba active as well as the topologically non-trivial state. So if we make a phase diagram as a Rashba coefficient as a function of the electric field, then we can find that the small electric field, we have an insulating state. If we have a large electric field, is a metallic state, and also we can go from a weak Rashba to a strong Rashba, and also from the bulk KCdBi to a, if we go to the confinement to the 2D version of it, then we can get a kind of topological H state and strong Rashba in the 2D layered version of the KCdBi. Okay. So this is the part summary of this part. Now, if we go to the second part, where we can we design the gap to the gapless crossover by tuning the interactions, or in more specifically the spin orbit coupling interaction. So technically, if we have a band inversion situation, if we apply the spin orbit coupling, then either we open up a gap with a topological insulator, which is a bulk gap topological surface states, or it is a wild semi-metal where you have a degenerate bulk state in a selected points in the momentum space. And all these things are basically symmetry tuned, where it is a protected time reversal and inversion, where is a in a wild semi-metal broken time reversal or inversion symmetry. So technically is a symmetry tuned crossover from this state to this state. Can we do this kind of transition by tuning the spin orbit coupling strength? Experimentally, how one can realize that, suppose I dope the system from a small spin orbit element to a large spin orbit element, technically I can tune the strength of the spin orbit coupling, although we have also did this thing with the experimental colleague, and we show that the extrinsic to intrinsic anomalous Hall conductivity we can enhance by this chemical doping. However, we can also do a theoretical way, since we are doing in an ab initio level, we can tune the interaction as per our own wish, and we can do that. So, what is this? So, the system that I chosen is a chalcopyrite system, is a ternary alloy, and this is the AgSnX X2. X is basically either nitrogen or phosphorus. For this case, we choose a two different system for a reason, and both are crystallized in a zinc blende structure, where the Ag mercury and the tin are surrounded by the tetrahedral unit by the X element. Now, this is very similar to a standard ZNS structure. Only difference is that is a cubic system, it is a tetragonal, it is a basically the C by A ratio is not, C and A is not 1, and also it is a non-centrosymmetric structure. Therefore, actually we can use the standard the inversion of the S and P, which is known for the mercury telluride, to this system as well to identify the band inversion. So, let me skip this thing. Okay. Now, if we look at the band structure, in the absence and the presence of the spin orbit coupling, we can see that in the presence of spin orbit coupling there is a nice crossing very close to the Fermi energy, and if we do the projected band structure, then we can see it is basically the inverted band structure in the case of the nitrogen system. However, in the case of this phosphorus system, if we do the similar thing, then we can see a very small kind of pocket. However, there is no crossing in the band, and is also the projected band structure shows is also is a inverted situation. So, that means in the case of the nitrogen, it looks like a wild crossing, while in the case of the phosphorus is a gap system, and it looks like a topological insulator kind of thing. Now, if we look at do the detailed topological investigation of the nitrogen system, and we indeed found there is a kind of there is a wild crossing, and there is a connected Fermi arcs, and the source and sink like the Berry curvature, and also the arc related bands in all these feature signifies that is typically the inversion symmetry broken wild semi-metal. Whereas in the phosphorus is a typical the topological insulator with a strong topological feature and the odd number of Dirac crossing in the surface states. Now, the point is this nitrogen is a topological wild semi-metal, whereas the phosphorus is a topological insulator. What I can do basically, the nitrogen goes to phosphorus. Now, if we put on the spin orbit coupling and try to tune the spin orbit coupling strength, what we can plot that if we increase the strength of the spin orbit coupling and we plot the band structure, you can see that if we increase the spin orbit coupling strength thrice, then is the open gap in the case of the nitrogen. Similarly, in the case of the phosphorus, if we decrease the spin orbit coupling strength, then we can close the gap and can a kind of band crossing in this case. Technically, this band and this band is very similar or equivalent, whereas the band and this band is equivalent. So, I can actually tune the strength of the spin orbit coupling can go from the gapless topological phase to gapped topological phase for the nitrogen as well as for the phosphorus by the reverse tuning. And now, one can say that how we can do this thing. Technically, there is a strong hybridization of the mercury band with the X or means nitrogen or phosphorus p band. So, that means when I am changing the spin orbit coupling strength, that means I am actually affecting the mercury bands, and since there is a strong hybridization of the phosphorus, that is why when I am changing the nitrogen to phosphorus, technically I am changing the strength of the spin orbit coupling. Okay. So, here what we can show, by tuning the spin orbit coupling strength, we can design the topological phases, can go from the gapped to a gapless. even in the same system. Okay. So let's move to the magnetic case where we can they have a wild nodal system and we can tune the anomalous Hall states by strain or the thin film geometry. Okay, I need not to introduce the nodal line, is already introduced by the previous speaker in detail. Okay, so there is a okay, let me just brief one thing. Okay, we can have a kind of gapless nodal line. Also, we can have a gapped nodal line. Usually, the spin orbit coupling breaks the gap in the or usually breaks the gapless nodal line into a gapped nodal line system. However, there are examples where even in the presence of the spin orbit coupling, the gapless nodal line still protected, and usually this protection comes from the non-symmetric symmetry, presence of the non-symmetric symmetry. And all these keys are the kind of time reversal intact system. So can we do the same kind of protection of the wild nodal line in the presence of the spin orbit, in the presence of the non-symmetric symmetry, but in the case of the broken time reversal symmetry? So this, okay, just to give a brief understanding, in the case of the non-symmetric symmetry means either I have a glide symmetry or screw where I have a mirror combined with the translation or rotation combined with the translation, and we can understand the degeneracy by just band folding mechanism. If we just fold the band, technically you can get a kind of degenerate bands, points in the band structure spectrum. Okay. So what we base chosen, this is the same chalcopyrite system, but is now MnGAS2, where the Mn is the magnetic. It is still is a non-centrosymmetric and the non-symmetric symmetry. We have a glide rotation and the mirror in addition to the pure rotational symmetry. If we look, if we look at the experiment side, there is a paramagnetic to ferromagnetic transition, and also is a kind of metallic resistance. And if we look at the anomalous Hall resistance, there is some sort of anomaly from the anomaly from the experimental side. So what we did, I don't know why the resolution is so bad. It is because of PDF, I guess. Okay, sorry for the very bad resolution. Technically, you can get, I don't know whether it is clear. Okay. Okay, so it is a spin orbit coupled band where you can get a kind of loop shape in the very close to the Fermi energy. And now if we plot, this is you have a two while crossing, and if we plot the if we calculate the nodal line is a kind of ring shaped, and it is connected by the two while points, and all these signatures are there with a drum hash kind of surface states. Now we can also, okay, now it's so bad. Okay, so our argument is that the protection is because of the non-symmetric symmetry. Now what we did is technically we displace the germanium atom, which basically breaks the mirror symmetry, and as a result you can see there is open up a gap. So that means it's confirmed that is symmetry that non-symmetric symmetry is actually protecting this gap, gapless feature of the nodal line. Now, since we know there is a anomaly in the anomalous Hall conductance, we calculate the anomalous Hall conductivity, and we see this indeed the Berry curvature driven anomalous Hall conductivity, which is almost 70, is very high. Is not very high, but is a reasonable. Interesting point is that now if we kind of strain the geometry by mimicking the thin film situation, we can enhance the anomalous Hall conductivity, which also shown here. If we can in bulk and is a thin film version, we enhance the anomalous Hall conductivity, which is enhanced due to the enhancement of the Berry curvature in the momentum space. Okay. So 2 minutes, 1 minute. Okay. So last, what I am going to show, if we can also design the Berry curvature by the heterostructure engineering, and this heterostructure is designed by the cadmium fluoride, and the chromium triiodide, which is a magnetic, it is a magnetic system, and where it is a non-magnetic. So let me skip this part. Okay, this cadmium fluoride is a topological metal, which is a massive Dirac system, whereas the chromium triiodide is a ferromagnetic system, which is a trivial in terms of the band topological perspective. So what we did, we basically designed the heterostructure different monolayer, bilayer, trilayer, and also different kind of bilayer or trilayer by changing the number of layers of this cadmium and cadmium layer and the chromium layer. And what we did, let me skip this. Okay, let me skip this. So what is the interesting thing is that there is a Dirac kind of massive Dirac point coming from the cadmium, whereas these bands are coming from the chromium. Now with the spin orbit coupling also, this is a very similar. This is before the heterostructure design. Now if we design the heterostructure, if we go to the okay, let me this one. If we do the heterostructure with a spin orbit coupling, then we can see there is a strong hybridization of these bands close to the Fermi energy, and this is basically because of the heterostructure designing. And if we look at the projected band, and it's indeed a kind of inversion between the cadmium 5a states and iodine 5p states. And also we calculate the Fermi surface, and that Fermi surface texture and the size also depends on the heterostructure engineering, how we can design the heterostructure, how many the layers are there. So in both of the case, there is no anomalous Hall conductance. However, independently for the chromium and cadmium, however, if we calculate the anomalous Hall conductivity for the heterostructure, you can see nice anomalous Hall conductance at the Fermi energy, whereas in the case of it is increasing in the case at the point of the crossing, and this is coming purely from the Berry curvature feature. Okay, let me skip. And also we calculate the transition temperature in the case of the heterostructure, which is coming out around 0.9 of the parent chromium triiodide transition temperature, and also the Fermi velocity is very high, close to the 10 to the power 6 meter per second. Okay, so okay, now how we can tune this band structure which is away from the Fermi energy? If we add this electric field, technically we can pull it down close to the Fermi energy by a moderate electric field. So and this is all the heterostructure. I am not going into the detail. So last summary is that actually you can do the gate voltage controlling of the massive Dirac, and can bring to the close to the Fermi energy for useful for the transport. So we basically covered the 4 different type of designing principle for the non-magnetic as well as the magnetic, which I can tune the interaction or the geometry or the to tune the topological phases. So at the end, thanks, and okay.
Thank you, so the session is open for questions.
Yeah.
So I'm just wondering about the first part of your talk. You calculated the edge states and everything. So I was wondering, are they edge state or surface state?
Okay.
I mean,
so
this is 3 dimension.
3 dimension, there is a surface states.
Right.
When I make it a 2D layer, there is a edge states.
No, but your calculations are done on slabs.
Slabs. Okay, I'm going to that thing. So we basically have a 3D system. From there, we cut one layer and put a kind of slabbing by making a vacuum, and then that part is calculated. So technically it's a slab calculation.
Okay. And about your third part of your talk, where you talked about chromium iodide. So you just calculated on single layer of chromium iodide? Probably
Okay.
not. Double layer and tri
Okay.
layers are also
Yeah. So there is a different type of heterostructure. In this case, the one cadmium fluoride layer, one chromium iodide layer, and here I have a 2 cadmium layer, 1 chromium layer. Here I have a 2 chromium layer, 1 cadmium layer.
So maybe for BL2 case or TL2 case, maybe they are not ferromagnetic anymore.
They are not ferromagnetic anymore. Yeah.
Because it is ferromagnetic in single layer only.
Yes, that's
now
true.
It become antiferro, right?
Yeah, that's true.
So do you see any consequence of that?
Okay, we have not checked that if we change the, say for example, this to this, if we make a kind of ferro antiferro, what is the difference? That we have not checked.
Okay, thank you.
Thank you, sir, for the wonderful talk. So in section 2, you took two compounds with
Yes.
nitrogen and phosphorus.
Correct.
And you have shown band gap closing and band gap opening.
Yeah.
Yes. So you are changing the spin orbit coupling strength individually.
Yes.
So how are you tuning this spin orbit coupling?
Okay. So since okay, we are doing the electronic structure calculation. So technically, if we have a kind of, I have a kind of this kind of Hamiltonian encoded in the system. So this lambda is the parent strength of the spin orbit coupling that we cannot change. It is the atomic property that we cannot change. But now if we introduce a kind of a parameter in front of that, and now if we manipulate this parameter, effectively I am changing this, that's why it is written as a lambda, 1.2 lambda, 3 lambda. I am not saying that this is the strength of the spin orbit coupling. I am just increasing a kind of scaling factor of the spin orbit coupling. And that is we basically manipulated in by hand in the calculation so that we can capture this feature. But experimentally, yes, you can do, but not like this fine tuning, but changing the element, like one of the case we change the platinum doped with the iridium. So if we increase the iridium concentration, so technically I am increasing the strength of the spin orbit coupling in that particular system.
Okay, thank you.
Yeah.
Thank
Yeah.
you for this interesting talk. I have a very simple understanding and experimental question.
Yeah.
So regarding this margarine N2 and margarine phosphorus,
Yes.
so if you really do any bulk measurements to find out the gap, will it be possible?
Okay, so okay, let me go to this gap. Means this gap you are talking about, right?
Yes.
Yeah. So this is a bulk band structure for the nitrogen, and this is a bulk band structure for the phosphorus. Now if we look at the this band structure, so is a very small kind of hole here. So you will get this kind of feature in the experiment, obviously. And in the case of this, there is a clear cut not gap state. So if you do the transport in the bulk system, you do see these one is the gapped and is not and is gapless.
Yeah, so then can I okay, very fast.
Okay.
So that means that now you in your calculation, basically you are tuning your lambda, which
Yes.
is nice. So now my question is that if you can your calculation also make some kind of straining?
Yeah, okay. So yeah, that we can do, but here we have not explored this part. But in the next system where MNGAS2, actually we did a straining, which why you can ask why I am straining doing. Actually there is an experiment which on the thin film. So in the thin film is a strain system. So try to mimic the thin film in our calculation by that strain. Is not actually the thin film calculation, but just geometry straining thing we have done this thing, and we show that if we do that, we can enhance the anomalous Hall conductivity.
Thank you.
Thanks.
So for